All right, so let's continue from where we left off last time. We did a few examples of equilibrium of rigid bodies. There was one more example left on that sheet that I handed out last time. So let's do that, okay? So this here, is a circular 3/4 of a circle rod that is resting on these two supports here without any friction. And it's being held at this point, by there is a collar here that is free to slide on this rod and is held by this pin here by this wire. Okay. Again, this is a kind of a toy example just to help us exercise our concepts of equilibrium and stuff like that. I don't think it's related to anything, actually physical. Okay. So our interest is in computing the reaction here, and the tension in this wire. So what are we drawing the free body diagram of? Drawing the free body diagram, cut this rod out of everything else. And we're going to draw its free body diagram. Okay. This angle here is 90 degrees. And this line is kind of this line is straight here all the way. Okay, so we've cut this out. What are the forces acting on it? Okay. Can somebody use the microphone and what are the forces acting on this free body diagram?
Is it on force A or point A?
Right, so there is how many forces at point A?
X and a Y.
Right, there is an X component and a Y component, but because this is a frictionless surface, there is only the force that is perpendicular to it. Okay, that force itself will have a horizontal and vertical component, but we'll just call that N sub A because we know that there isn't an independent other component. Okay, there's only a component that is perpendicular to that surface. And similarly, there's a force here that is perpendicular to this surface. And what else? So we have to draw a force wherever we made a cut. Okay, so we also made a cut through here. So we have to draw a force there. And that is the tension. We'll call that T sub B. Okay. And then there is this externally applied force. This angle is 60 degrees. And this externally applied force is 25 newtons. Okay. Also label the points here. This is A, B, A, that one's D, I'm sorry. So this is N sub D. This is B. These angles are 45 degrees each. Okay, so that's our free body diagram. Okay. Any questions up to this point? Okay, so our next step is count the unknowns and equations, right? So how many unknowns and how many equations of equilibrium? So how many unknowns, anyone?
There are 3.
Three unknowns, NA, ND, and T sub B, three unknowns, okay? And for this rigid body, we have three equations of equilibrium. Okay, like I said in the class, at this point, this seems like a trivial thing to do, but very soon we'll see when this isn't, the counting stuff isn't that trivial, okay? Okay, so now the next step is to write equations of equilibrium. And we can set out to write some of the forces in the X, some of the forces in the Y, and so on. But we want to see, is there some equation of equilibrium I can write, that'll get me an unknown immediately, right? So any ideas?
Taking a moment about the center.
Taking the moment about the center, okay, we'll call that O. Okay, so what does that kill? TB goes right through there. So TB will have, no, we kill TB. But NA and ND will both have moments about there, right? So it is a legitimate equation, but can we find one that kills two unknowns and leaves us only with one?
Was it the y-axis? Forces in the y-axis.
Force in the y-axis, are we thinking of this as x and this as y?
Yeah.
So if I do forces in the y-axis, NA is going to have a y component, ND is going to have a y component, TB is going to have a y component. So in fact, that involves all three.
You can change the order of the axis to the
Right.
degree.
Right, okay. So what are we doing then?
So if you do that, the thing is like you can put the 25 newtons and NA in the same x-axis and TB and ND in the y-axis. So
Right.
if you do x's, will be just 25 plus or minus NA equal to 0, and you can get NA.
Okay, so if I understand you right, let's do this. So I'm going to call this the x-axis and this the y-axis, okay? The 25 newtons not quite lined up with the y-axis because, that's 60 degrees and the y-axis is only 45 degrees away. So I'm going to call this the x-axis, that the y-axis, right? So instead of calling x horizontal and y vertical, I'm going to call this direction BD, I'm going to call that x. And then perpendicular to that, I'm going to call that y. So if I do some of the forces about that y-axis equals 0, so that with this direction being positive, okay? Everybody follow my notation here? So I'm calling this line BD, I'm calling that my x-axis, and then the line perpendicular to that, I'm calling it y. And then when I sum forces in the y, I'm taking that direction as positive, okay? So what does that
makes
give me?
sense. Mm-hmm.
What does that give me? So NA is parallel to the x-axis. It has no component there. TB is parallel to the x-axis, no component there. So what does that give me?
Would it be the 25 cosine of theta?
Right. So let's write the ND first. Okay. So it's ND because ND is in the y-axis, and then 25 newtons times what cosine of what angle?
Of 90 minus 60, so 30.
Well, what I'm looking for is this angle here, right? What I'm looking for is this angle here.
Yeah.
That whole thing is 60, and this much is 45. So this angle here is 60 degrees minus 45 degrees. That's 15 degrees, right? So what I'm doing is cosine 15 degrees, and that's a minus, and that's equal to 0, okay? Does that make sense? So the concept is really simple, that I'm writing an equation of equilibrium that gets rid of two unknowns and gets me one directly. But computing the angles and all that is a little bit tricky business that you just have to think about a little bit more. And any questions? Does it make sense? Okay, what else can I do? What other equation of equilibrium can I do that will
Some of the forces in the x direction.
I can do some of the forces in the x. That's perfectly legitimate, but that'll have NA and TB in it. Oh, some of the forces in this x. Well, that'll still have NA and TB in it, right? Which is again perfectly fine, but I want to write one first that's going to, get me one directly.
You could take a moment around where the points NA and ND meet.
Right, over here, right? If I extend this, I can do that here. Yes, and that'll give me TB directly, okay? So let's call this point some P or something. So I can do some of the moments about P equals 0, and that's perfectly good, right? You just need to be careful about calculating all those distances. Just not, I guess, too bad to do, right? What I'm going to do is I'm going to do some of the moments about D here, okay? I'm going to do some of the moments about D equals 0. Like that, okay? Why is that good? Because that gets rid of TB and ND, and I can get NA directly, okay? So what is the moment of NA about that point? So I can do various kinds of things, but I can do break this into a vertical component and a horizontal component and calculate that distance and do it that way. Or I can extend this line, and you see that this distance here is simply equal to R. So I can do just NA times R, and that rotation is clockwise, so I put a minus in front of it. Okay. The only other thing that's left is doing the moment of this 25 Newton force. So if I slide the 25 Newtons down to here, if I slide the 25 Newtons down to here, this angle again is 15 degrees. Okay. So the component of the 25 Newtons that's along the direction OD doesn't have any moment. So I just have to look at the component of the 25 Newtons that's along OA. Okay, so that'll be 25 Newtons cosine 15 degrees times R. And then that moment is counterclockwise, so that's a plus equals 0. So I can solve that and I get NA is, so this gives me NA and D is 25 Newtons cosine 15 degrees. And this gives me NA is 25 Newtons cosine 15 degrees. And then finally, I can do some of the moments of some of the forces in this new x direction. Doing this way is positive equals 0. So what does that give me? TB minus NA, right? And then the 25 Newtons has a force in that component in that direction, which is plus 25 Newtons sine 15 degrees equals 0. And I can solve that, okay? And like somebody said, you can also do the some of the moments about this other point. But okay, is that idea clear to everybody?
Yes.
Any questions? Okay. So before we get to the next example, we're going to talk a little bit about pulleys. So if I have a pulley that's fixed at this point, and I have a cable or a chain wrapped around it, and the radius of the pulley is R, and let's call this tension T1, this tension T2. Okay, so that's a pulley, and I have a cable or a chain wrapped around it. I'm just cutting the chain at these two places, and let's say that the tensions T1 and T2. Okay, now let's draw a free body diagram of just the cable. So I'm cutting it out like over here, drawing free body diagram of that. Let's call this point O. So that distance is R, and that distance is R also. And actually, and this tension is T1, and this tension is T2. Okay, now if there's no friction between the chain and the pulley, then there are no forces at this interface here, right? If there is friction, then there will be forces at this interface here. But so in the absence of friction, or negligible friction between the pulley and the cable, okay, there are no other forces. So if I do sum of the moments about R equals 0, there's forces like this, there's normal forces, but there's no tangential forces. Okay, all the normal forces will just pass through this point, right? So these normal forces are what are keeping it in equilibrium, but there's no friction forces. And normal forces all pass through this point. So if I do some of the moments about R, then I just get T1 times R minus T2 times R equals 0. So I get T1 equals T2. Okay. So the conclusion is, if no friction, so in a frictionless pulley, tension on either side equal. Okay, that's a fact, and that comes from equilibrium of the cable itself. Does that make sense? Any questions? So whenever we have a pulley that is frictionless, then we know that the tension on either side of the pulley is the same. A little bit further down the line, we'll see how to account for friction between the cable and the pulley. Okay. All right. So with that background, let's do this example. Okay. And going forward, we're not going to look at all the examples in a lot of detail, but just we'll just draw the free body diagram, count unknowns and equations, identify which equation of equilibrium to write, and then we'll keep moving on, not actually write the equations of equilibrium, but you should go back and at least try to write them out just to make sure you understand the concepts, okay? All right, so here, this pulley is frictionless, so the tension here and here are equal, and there's a pin here. We want to find out what that tension is and what the reaction in that pin is, okay? So what's the free body diagram I'm going to draw? we're going to cut it over here and cut through there and draw the free body diagram of that. Okay, so free body diagram is cut through there. So this distance is 15 inches. And I have 8 inches, 8 inches, and 20 inches. Okay. So what are the forces acting on this? I have this, how much is that? 30-pound force. What else? What force is at C?
There are two reaction forces,
Right.
Cx and Cy,
I'm
as
just
well as
going to
a
call it
moment.
Cx and Cy. There's no moment because that's a pin. Okay.
Okay, I see. Yes.
That's a pin, so the only reactions are Cx and Cy. Okay. Then there is a tension in this direction. So I connect those two lines. There is a tension in this direction, call that T, and there is a tension in this direction, we'll call that T. Okay. Any questions on the free body diagram?
Why is CX pointing to the right, not the left?
So I don't know what the magnitude of Cx is. It's an unknown, right? So by convention, I'm drawing it as though it's in the positive direction. Okay. Your intuition probably tells you that it's eventually going to point in the left direction. Maybe that's the case. If that's the case, I'll get a negative answer for Cx. Okay. So if it's just my convention that any unknown force, I draw it in the positive direction. And then if it turns out to be in the opposite direction, I'll just get a negative sign. Does that answer your question?
So where you draw it doesn't matter. It's just what answer you get at the end, if it's
Right.
positive or negative.
Right, right. If I have it in the right orientation, which sign it points along is, it'll come out in the answer.
Okay.
Okay, so if somehow my intuition tells me that I expect it to be pointing in the left, and then I should get a negative sign. I expect to get a negative sign. If I don't, then I should ask, am I making a mistake in the calculation, or was my intuition not informed correctly? Okay. All right, so then we count here. Okay, so 3 unknowns. T, Cx, and Cy, and then 3 equations. Okay, this seems almost automatic at this point. Like I said, it'll become less trivial a little bit down the line. Okay, so what equation of equilibrium to write? So let's label the points. This is A, B, C, and D. Okay, what's a good equation of equilibrium to write?
Some of the Y forces.
So if we call this X and this Y, if I do some of the Y forces, that's going to have T and Cy in it, right? Again, it's a legitimate equation, but I don't want to write that immediately because I'm going to have to deal with 2 unknowns. So I'm going to see if I can write an equation that involves only 1 unknown. What else can I do?
You can take a moment about
Someone
C
said
because
moment
there's
about
2
C.
unknowns.
Right. So I can do a moment about C equals 0. Okay. That gets rid of Cx and Cy. Right. What else can I do? That'll get rid of 2 unknowns.
Can you do moment about D? Would that get
Moment
rid of
about D. Right. Excellent. So do moments about D equals 0. And that'll get rid of T and Cy, right? Then solve for Cx. In fact, if I do that, I'll get what? CX times 15 inches. That's counterclockwise, minus 30 pounds times 28 inches equals 0, and I can solve for CX directly. What if we did that the first one, some of the moments about C, right? I'm going to have, no, sorry. This is also a plus, right? And your intuition earlier was right. We're going to get a negative answer for CX, right? Both the moments are counterclockwise. Okay, so what about the other one? Let's do some of the moments about C equals 0. What does that give us? So remember that let's draw some directions here, okay? So this is 28, this is 15, and the square root of 28 squared plus 15 squared. Plus 15 squared. That is 31.8. 31.8. Okay. And this one's 36. That one's 15 again. So if I do 36 squared plus 15 squared. (36 squared plus 15 squared). Square root of that is 39. Okay. So if I do some of the moments about C, then what do I get? Let's do this T first. Okay, so it's T times the horizontal component of T has no moment about C because it goes right through. I only have to do the vertical component. So what is the vertical component? Times 15 over 39. Okay, everybody okay with that? Okay, times the distance is 36 inches. And that's clockwise, so minus. And then minus this other T now. T times 15 over 31.8 times 28 inches. Okay. And then plus 30 pounds times 28 inches equals 0. So the only unknown in that equation is T, and we can solve. And having done these two, in order to get, the only thing we haven't gotten yet is Cy, so we can just do some other forces in the y equals 0 like this, and that'll give me Cy. Okay. Any questions on this one? So like I said, yes, go ahead.
Well, not more of a question. There are students in the chat saying that you might have labeled tension B wrong.
Oh yes, the tension at B.
Yeah.
Okay, I haven't been paying attention to my chat. Thank you for bringing it up. Let me. Yeah. Okay, sorry. Yes, I do see it now. Okay, so I see a number of questions here. Okay, so would somebody like to ask me the question first, instead of my going back and reading all these? So one question is why the pulley, would the pulley then just act like a frictionless surface? Yes, it just acts like a frictionless surface. Yes. Okay. If there's no friction between the wheel of the pulley and the rope, then yes, it's exactly like a frictionless surface. Okay, I answered that one. You label tension at B wrong.
I believe
Oh,
they're
oh,
saying
okay. Right.
Yeah.
Okay, so this you're actually right. So sorry, let me correct all that. Okay, thank you. So okay, sorry. So this is actually like this. That is the tension. The directions are 20 and 15, right? So this is actually 25. Comes out to be a nice number. I should have known when I didn't get a nice number there, but okay, so let's correct this. Thank you so much. Okay, so and this point is what is B. Fortunately, it doesn't change a lot of things that we did here. So this one is 15 over 25. 15 over 25 times 20. Okay. Yes, thank you so much. That corrects that. I don't think there's anything else that changes. Any questions? All right, I'll pay attention to my chat too going forward. All right, I hope that screw up didn't result in too much confusion. Okay. All right. Let's do this one. We'll try to go through the rest of them. I keep saying this, but I get into the details. So let's try to, go through this one somewhat quickly. Okay. So we want to find the reaction here. We want to find the reaction here and the tension in this wire. This is what we want to do. So we draw a free body diagram of all this. Cut it around here, right? So first step is free body diagram. Let's mark some dimensions here. This distance is 6 inches. This distance is 20 inches. This distance is 10 inches. Okay. And then we have a 100-pound force here, and another 100-pound force here. And those distances are 4 inches, 12 inches, and 4 inches. Okay, all right. So what are the reactions now? What are the other forces that I have to be concerned about?
the vertical reaction force at points A and C because they're both rollers.
They're both rollers. So
Oh,
at A and C, let's call it AY, or I call it N sub A or something. And we'll call this N sub C. And then along the line connecting this and this, there is the tension T. And it's maybe helpful to mark the directions here, okay? So how much is this? This is 14 inches this way, right? And this way, how much is it? How much is the vertical distance here? How do I get that?
by using similar triangles.
Similar triangles, right? So it's 6 divided by 6 inches divided by 20 inches times 10 inches. So that's 3 inches, right? So this here is 3 inches. So this is 3. And this is the square root of 3 squared plus 14 squared. Okay. 3 plus 14 squared equals 14.3. Okay. All right. So that gives us all the information we need to eventually write equations of equilibrium. Okay. Any questions up to this point? So there are these small things like getting the right distance and getting the right angle and things like that. That is simply geometry, right? This isn't the core of statics. These are just details we have to do along the way. So you got to remember at the end that ultimately we want to do some of the forces, some of the moments. All these distances and all that are tricky little things we have to calculate along the way. Shouldn't let that kind of stuff throw us off our main course, right? So any questions on these little details, how I got all these numbers? Okay, so the next step is to count. Okay, remains a trivial step, 3 equations and 3 unknowns. Okay, soon to get non-trivial. And so if I get on to writing equations of equilibrium, okay, what can I do first?
Can you give the
Any-
moment about C or A?
If I do a moment about C, what unknowns are going to go? What unknowns am I killing?
A.
Just
not-
just NC. I'm just killing NC, right? If I do moments about C, I'm just killing NC. If I do moments about A, I'm just killing AY.
Could we do
So
the point where, sorry, could we do the point where NC and AY intersect? Is that possible?
right. So if I take this intersection point, right? Let's call that O, just to give it a name. You see that if I do some of the moments about O, then that gets rid of NA and NC, right? And then so that'll, if I solve this, that'll give me T. Okay. Should we write that equation of equilibrium, or should we just go on to the next example? Not a great environment for polling, but well, the time I spend waiting, maybe I can actually write the equation of equilibrium. Well, let's just do it, okay? I think having more practice is not too terrible. So I'm going to do some of the moments about O, okay? The only unknown that has, so let's start with this 100-pound force, okay? 100-pound force, 100 pounds times what's the distance, anyone?
4 inches?
4 inches. Okay, is that positive or negative?
Negative?
Negative, because that's clockwise, okay? Same way, it's minus 100 pounds times 16 inches for this one, okay? That leaves me only with T, right? So, T, I have to break it down into a horizontal component and a vertical component, and then calculate the distance for the horizontal component and the distance for the vertical component. Instead, I can do that, okay? I get the same answer. Instead, what I'm going to do is I'm just going to slide it over to here, okay? I'm just going to slide it over to here so that well, in fact, I still have to do both. Maybe just the distances are easier. So, okay, so I'm going to slide it over to here. And so it's going to be T times the horizontal component, which is 14 over 14.3, okay, times the distance is 10 inches. Okay, so horizontal component, the distance is 10 inches. And that's counterclockwise. So that's a plus. and then plus the vertical, the vertical component is t times 3 over 14.3 times that distance is 20 inches. But the vertical component has a clockwise moment, so that's a minus, equals 0. Okay, so I have this one equation in the one unknown t, and I can solve for it. Once I have t, I can do some of the forces in the x equals 0. That'll give me nc, and then I can do some of the forces in the y equals 0. And that'll give me na. Okay. Any questions? So
One
yes,
quick
go ahead.
one.
Yes.
Does the denominator say 14.3 or 14 times 3?
It's 14.3. At 14.3, the 14.3 comes from this distance here, okay? This hypotenuse here, 14.3. Okay?
Okay.
Any other questions?
How is the distance 10 inches from the component?
Right. So if I want having slid this t down here, right? If I break it down into horizontal and vertical components, okay? The horizontal component, if I look at the moment it produces about, the perpendicular distance is this much, right? And for the vertical component, the horizontal distance is this much. You see that? To answer your question, or is that not clear yet?
Yeah.
Okay. And so what I'm going to do is maybe skip this next one. We'll do that in class on Wednesday. And let's do this one instead, okay? And whatever I haven't been able to complete, we'll do in class on Wednesday. Okay, so a slender rod AB, weight W, is attached to blocks A and B, which move freely, okay? No friction in these slots, no friction here, no friction here, okay? Blocks are connected by a cord, goes over a pulley, no tension and no friction in the pulley either. Calculate the tension and the reactions, okay? So we're gonna cut this bar out of here and draw its free body diagram. So that's our first step, is drawing our free body diagram. Okay, theta is, it's just a variable. It's just a symbolic quantity. So I'm just call that theta. So this distance is L. This distance is theta. And what are the forces acting on it? I have this reaction here that is N sub A. I have this reaction here that's N sub B. Okay, I also have the tension here and the tension here when I make the cut. And I have the weight that's acting right in the middle. Okay, so note W and theta are known symbolic quantities, okay? They're not unknowns. So we're going to compute everything else in terms of W and theta, right? So the fact that they're symbols and not numbers shouldn't throw you off, okay? You can think of W as, 100 pounds and theta as 30 degrees or something. That's, it's not given like that, but it's known symbolic quantities, okay? So if we count, how many unknowns do we have? 3 unknowns. NA, NB, and T, and 3 equations. So we can solve, right? So I'm going to do, okay, Next step is writing the equations of equilibrium. Okay. So what's a good equation of equilibrium to write?
The moment.
The moment about where?
About
Should
the
we take a
axle.
moment?
About the axle and like the corny, the left corny.
About here, you're saying? About here? Oh, the axle of
Yeah.
the pulley. Right. So what
Yeah,
happens
that.
if I do that? That kills the T, but leaves both NA and NB, right?
Yeah.
Which is perfectly legitimate equation to write, but I'm just, being impatient. And I'm saying, I don't want to wait till I write all the equations before I can solve. Let me see if there's an equation that'll give me an unknown right away. Any other ideas?
Appointing NA and NB.
If I can do the moment about the point that at the point of intersection of NA and NB, we'll call that O, right? So if I do some of the moments about O, that gets rid of both NA and NB, so I can solve for T directly, okay? So let's just write that equation of equilibrium and then we'll stop, okay? So what does that give me? W times, what's the distance? It's 1/2 of L cosine theta, right? And that's clockwise, so that's positive. I'm sorry, that's counterclockwise, so it's positive. And then this T, so it's minus T times L cosine theta. That's clockwise, so it's negative. And then I do this T, that's plus T times L sine theta equals 0. So I can solve for T in terms of W here. Okay? And then if I do some of the forces in the X, I can get an A. And then if I do some of the forces in the Y, I can get an B. Okay? Any questions? All right, so I hope that you're able to see the repetitive nature of this, right? We're just doing the same thing over and over. And once we get good at this, then we can start doing more involved things with multiple free body diagrams and stuff like that, okay? So we're going to spend one more class on Wednesday just doing this kind of practice, just to get comfortable with this. So there are two things to this. What are the core steps? It's right. It's drawing the free body diagram, counting the unknowns and equations, figuring out what equations of equilibrium to write. And then there's details like how to calculate this distance and doing trigonometry and stuff like that. So you've got to separate the core from the details, right? And, just comes with practice. So thank you again for accommodating this remote session. Hopefully I see you in person in class on Wednesday. Any last minute questions before we stop? All right. Okay. Thank you very much. Oh, question. Okay.
Would this recording be posted on UB Learns?
I'm going to try to do that.
Thank you,
Okay.
Professor.
Yeah, I'm not sure how quickly I can do it, but I'm going to try to do that. Any other questions? All right. Thank you, everyone, again. I'll hopefully see you in person on Wednesday.
Thank you.